Hello everyone and welcome to another Stat 437 lecture video. In today's video, we're going to be looking at an example analysis for linear mixed effects models in R, where we're analyzing some data from the 6 Cities study, which was a study that investigated the lung growth in children and specifically was looking at sort of the impacts of air pollution on these kids as well as other factors and how their lungs developed. Okay, so what we're going to do is we're going to take the methods that we've been talking about over the last few lectures and we're going to just try to apply them. So as always, the data that we're going to be analyzing in this lecture is available on the course website, as well as any of the code that we're using here. All of that should be available online. So, I advise you to check that out and to work along with me here if you can, and, to experiment with it a little bit more than what we just talked about today. But with that, I will open up R. And we can begin talking about the data that we're going to be analyzing here today. So the first thing is that we're actually going to be using the exact same package that we were used to using at the start of the term here. So it's the nlme package, and I'm going to load it in, and you should all have this installed by now, but if not, again, you can just call install packages, and that should work out well for you. The other thing is that I'm going to pull in the data here, and so again, this air pollution data set is available on the course website, and as is this call to load in the data if you look in that data import helper file. So I'm just going to load that in, and then we can take a look at what this data actually looks like. So I'm going to view the air pollution here, and you can see that we have a column for the ID, which is of course the individual's ID. We have height and age, and then baseline height and baseline age. So you can see that for individual 1, their height at the first time is 1.2 and their age is this 9.3415. And then the baseline values take on those values, right? So at time 1, the baseline height and baseline age are just equal to the height and the age, but then as you go on, those remain constant over time. And then we have this log FEV1, and that's going to be a measure of the respiratory health or the lung health of an individual. And so the idea is that we want to model this as the outcome, and we want to see how it's related to the height and the age, as well as the baseline height and the baseline age for any given individual. Now, it's been shown in previous research that the outcome here is related to the age and the log of height on a linear scale. And so we're going to use that to sort of justify this use of a continuous model where we're assuming sort of this linear structure between those variables. So I'm going to come in here and I'm actually just going to start by building out the model that we're going to be working with, or at least the first model that we're going to be working with. So I'll call it model 1, and we're going to use the LME function, so the linear mixed effects function. And it's going to be quite similar to the other modeling functions we've used, but in this case we want to specify fixed and random instead of specifying one single formula. So with our fixed formula, what we're going to do is specify a two-sided formula where we specify the outcome on the first side. So in this case, that's the log FEV1. And on the other side, we want to specify any fixed effects terms that we want in our model. So let's say that we just include all of the main effects. So that'll be age, the log of height, the baseline age, as well as the log of baseline height. Right? So this is just going to be any sort of regression formula where all of your fixed effects are included. For random, we're going to do a similar thing, but instead of including a two-sided formula, we're actually just going to include a one-sided formula. So instead of having our outcome on the left-hand side, we don't put anything on the left-hand side. We start with the tilde, and then we include just the values that we want random effects for. So to begin, I'm just going to specify random effects for the age, and then we want to include sort of our conditioning variable here. So we're going to nest that inside of ID, right? And what this is going to say is that for each individual, let's fit a random intercept, because there's always the intercept included, and a random slope for the age term. And this is going to be within each individual. So we can think about this as sort of the random intercept model that we've been talking about, right? Now, one thing to note while we're here is that we're specifying age as the time variable, right? But you can see that the ages here weren't standardized, right? So individual 1 started when they were 9.3 years old, individual 2 when they were 6.5 years old, individual 3 at 6.9, and so on, right? And so instead of measuring sort of time from baseline, what we're going to be doing is measuring the actual age as our sort of interest. And so in this sense, you can think about people enrolling at different times because they're different ages when they enroll, and then just measuring time passing from there. If you wanted to, you could, of course, define time to be the sort of age that they are minus their baseline age, and that's going to give you how long were they enrolled in the study. But I think from a scientific perspective, these kids lived in the same place for their whole life so far, and so we're going to think that it's actually related to how long have they been alive, not how long have they been under observation, right? And so, we're sort of talking in real terms about the different ways that you can think about coding time in a model, but that's what we're going to do here. After you've specified your fixed and random effects, mostly that's all you have to do. Now we can specify this correlation parameter optionally, and this is going to sort of specify the GI model for us, okay? So we know that we want GI to be equal to sigma squared times I. That's what we've said we'll use in this course. And in fact, the correlation defaults to that value. So I'm going to specify it to be null, which is going to just give its default value. But we could think about using a more complex structure here, but for now, we can leave that as default. We'll specify the method, which is either ML or restricted maximum likelihood, right? So we'll leave that as ML, and then we just need to specify our data. So that'll be our air pollution. We can fit the model, and if we take a look at the summary of model 1, well, the summary is going to look quite familiar because, sort of all of these regression type methods output a similar model summary. So we can see at the top, we get some model fit criteria. Then we get some information about our random effects, which is going to include the parameters needed to fit those distributions. So you can see we have our random intercept has this standard deviation. Our random slope term has this standard deviation. The two of them together have some fixed correlation. And then we have this residual estimate, which is actually an estimate for sigma. Then we have our fixed effects terms, right, which just look like a regression coefficient table. So there's the value, the standard error, test of significance, right? And then we have additional bits about our correlations and our residuals, the overall model fit, right? And so that's going to be sort of the standard output that you're used to looking at. And so let's, start talking about what is this model actually doing in this case, right? I think there are really 3 different ways that we can think about the outputs of this model. And so the first is to think about it in terms of a marginal model, right? So we saw in the previous lectures that we can think about just the expected value of Yij, which is taking the expectation over our whole thing and just sort of giving us the population average. And in this case, we're just going to be left with whatever the fixed effects terms that we've specified are, right? So that's going to be beta 0 times by beta 1, or plus beta 1 times by its age, plus beta 2 times by the log of height, plus beta 3 times by the baseline age, and then say beta 4 log of baseline height. Okay, so these 5 regression parameters sort of codify the marginal model, right? And so you could think about using this fixed effects terms here to talk about population averages, just as we did for marginal models. Now, the other bit that the linear mixed effects models give us that we didn't really see before, at least we haven't talked about explicitly before, is this ability to break down cross-sectional and longitudinal effects very specifically. And in this case, this model is going to give us the ability to do that quite nicely. So if you don't remember from the first introductory lecture, a cross-sectional effect is sort of like a longitudinal effect, except we're comparing 2 different groups of individuals at the same time, right? So at some time point, you might have a group of 70-year-olds, you might have a group of 50-year-olds, and we're comparing, are they different on their outcome at that time, right? Compare that to a longitudinal effect, which is you follow a group of 50-year-olds until they become 70, and you see within each individual what was the effect over time, right? And so we can think about either trying to identify cross-sectional effects or longitudinal effects, right? And so for the cross-sectional effects, if you think about what the expected value of yi1 is going to be, right? Well, at yi1, this baseline age and this age term are exactly the same, right? So we could say that this is going to be beta 0 plus, and then we could combine beta 1 plus beta 3 times by the age, and then we can do the same thing for the log of height, right? So that's going to be beta 2 plus beta 4 times by this log of height. Okay, so at time 1, because we know that this baseline age and this age are equal, we sort of can get these estimated values a little bit more in sort of a closed form here. Now, if you contrast this with trying to get a longitudinal effect, so let's say in this case, the difference between yij and yi1, right? If we want to know what the expected value is here, well, now when we subtract off this yi1, right, we're sort of subtracting off these baseline age terms, okay? So in this case, well, we see sort of the expected value of, this is going to be the difference between these two models that we have written up here, right? So beta 0 is going to cancel out. And then we're going to have we'll have this beta 0 is canceling out, as I mentioned. We'll have this beta 1 times age term, right? And then if we consider what we're subtracting off as the relevant term in this model down here, well, we'll have a beta 1 where here, this age is actually our baseline age, right? And this height is actually our baseline height. So we can express them in those terms, because now what we can see is we'll have beta 1 times age minus beta 1 times baseline age, right? So we'll have age minus base age. And then we'll have this beta 2 times log height. We can do a similar thing here, where we're going to have beta 2 times log height minus log of baseline height, okay? And now we have beta 3 times baseline age, but we also have that down here, and we have beta 4 times baseline height. We also have that down here. So those terms will cancel out. And so we're left with this difference of sort of beta 1 times by our change in age, and then beta 2 times by the change in log heights, right? And so what this means is that beta 1 is going to be interpreted as the longitudinal effect of age, and beta 2 is going to be the longitudinal effect of log height, right? So for every unit increase in age from over top of baseline age, we expect a beta 1 increase in our outcome. And for every unit increase in the log of height, we expect a beta 2 increase in the outcome. Okay, so this sort of gives the nice interpretation of these effects terms. And then correspondingly, what this means is that if we're thinking of beta 1 plus beta 3, well, this is going to be sort of the cross-sectional effect, right? Because this is what we're looking at as the effect of baseline height, and beta 2 plus beta 4 is going to be the cross-sectional effect, where it's looking at the log of baseline height. And so now what we can do is we can ask questions about, do the cross-sectional effects and the longitudinal effects meaningfully differ, right? Is a 1 unit increase in the baseline age, sort of comparing two different people who start the study at a different age, is that the same thing as 1 year passing in the study itself? Okay? And so that's going to let us test some interesting questions. And so I'll just pull in a few different questions over here that we've typed out that we might want to answer from here. And so the first question is going to be, what is the estimated change in outcome for a 1 year increase in age? Our second question is going to be, what is the expected change in outcome for a 10% increase in the height? Okay. And then the third question that we want to answer is, do the cross-sectional and longitudinal effects differ? Okay. So these questions are all sort of scientific interest insofar as, we might actually care about these in the real world, but they're going to be related to this discussion that we just had about how to interpret the model parameters here. All right. And so to actually answer this question, well, what's the estimated change in outcome for a 1 year increase in age, right? This is a longitudinal effect question here. And we just were talking about how beta 1 is the longitudinal effect of age, right? So if we have grown by 1 year, right? So if our age has increased by 1 year since when we enrolled in the study, then we're going to see that we get a beta 1 expected change in outcome. So the answer here is that this is going to be beta 1, right? Which if we pull back up our model summary here, and actually what I'm going to do is I'm going to call fixed effects on the model object here. So that's model 1. And this is just going to output our fixed effect estimates to be a little bit cleaner, right? So fixed effects, we said that we are looking for beta 1, which is this age effect here. And so the answer is going to be that sort of beta 1 is equal to this 0.023538. So what we're saying is that when age increases by 1 year, as you get 1 year older, we're expecting the log FEV1 to increase by 0.024, right? And so if you want to know what does the FEV1 increase by, right? How does that change? Well, it's going to change by the log of this value, which is going to be about 1.024. So it's going to say increase by about 2.4%, right? And so that's sort of what the longitudinal effect of age is. Now we can move on to height, and it's going to be a similar situation here. Now the reason we're asking for a 10% increase in height is because if we were to say increase the log height by 1, well, that's going to be someone sort of growing to be 3 times their size or 2.7 times their size. And so that's obviously not scientifically interesting, but someone's height increasing by 10% certainly does seem to have a meaningful effect, right? So if someone grows 10%, what is the impact on this FEV1? Well, if their height is increasing by 10%, then the log height is going to increase. Let's say if their height is going to increase by 10%, so it multiplies by 1.1. Well, then when we're looking at the log height, that's going to be the same thing as the log height having added on the log of 1.1, right? And so if we say that beta 2 was the longitudinal effect of the log height, then if we want to know a 10% increase in height, that's the same thing as saying log height increasing by log of 1.1 over the baseline height. Okay? And so I'll comment that out. But basically what we're saying there is that this is going to have an expected change of B2 in our case, right? So this B2 term times by the log of 1.1. All right, and that's going to have the impact on the log of FEV1, right? And so if we scroll back up to what our fixed effects terms here were, we can see that the log height has this 2.23 whatever here, right? And so if we want to know what is the impact of this on our outcome, we take the exponential of this, and you can see that it's going to be this 1.23762, whatever. So it's about a 24% increase. So what this means is that the aging by 1 year gives us an increase of our outcome by about 2.4% multiplicatively, whereas growing by 10% gives us a 24% increase on this. Okay? And so the last question here that we have before we start looking at some other bits with our model is, do the cross-sectional and longitudinal effects differ? All right, so as we were mentioning up above, the cross-sectional effect is going to be beta 1 plus beta 3 and beta 2 plus beta 4. And then the longitudinal effects were just beta 1 and beta 2. And so if we want to test this null hypothesis that the longitudinal effects and cross-sectional effects are the same, what we're going to need to do is zero out beta 3 and zero out beta 4, right? So this is going to be a test of the null hypothesis that H naught, say, is beta 3 equals beta 4 equals 0. B3 equals B4 equals 0, right? And if we remember, this is a likelihood-based procedure, and so we could fit this by using nested models, say, or we could fit this using our L matrix, right? So maybe what I'll do is I'll type out what this L matrix would have to be, but then we'll actually test it using an ANOVA version, right? So this L matrix we'd want to test where we select out beta 3 and we select out beta 4, and so that's going to be 0, 0, 0, 1, 0, and then the second row is going to be 0, 0, 0, 0, 1, right? And now we would want to test whether L times by beta hat is equal to 0, right? And so it's going to end up being a chi-square 2 distribution because there are 2 rows. It's rank 2. But the alternative way of doing it, because we have R open, is to fit a model 1 reduced, right? And so we can update the model 1. And what are we changing? Well, we're changing which fixed effects are in the model, right? Because we want to drop off the fixed effect for the baseline age and the fixed effect for the log of baseline height. Okay, so we can say update this model. Here we're going to change the fixed to be log that. And now in this case, we're just going to include age and log height. Okay, so we've dropped the other ones. The random effects and correlation can all stay the same. So if we fit this model 1 reduced, then we can call ANOVA on model 1 versus model 1 reduced. And we can see that we get this p-value of 0.0749, right? And so the the overarching, whether we choose to accept or reject is going to be based on whether we care about it at a 10% level or say a 5% level. But, there's actually some evidence that we might want to reject the null hypothesis here, which would conclude that the cross-sectional effects and longitudinal effects do in fact differ, or at least there's evidence that they might differ in these data. Okay, and so that's sort of how we could go about interpreting and testing some of these effects. And we're used to seeing this. We might not be used to talking about it in exactly these terms, but hopefully that's making a little bit of sense. And you should get a similar result if you had tested this using our Wald test here, right? And so having investigated sort of our fixed effects, the next obvious thing to do is to take a peek at our random effects. Okay, now recall that generally speaking, we want to use the restricted maximum likelihood when we're investigating our random effects. And so what I'll do is I'll say model 1 REML is going to be update of model 1, and we'll just use the method REML. Okay, and so now we have this model fit using REML, and we can take a look at the summary of our model 1 REML again. And in particular, we can take a look up. We scroll up above our coefficients that are output. We see this table here where we get a standard deviation estimate for our intercept and for our age, as well as a correlation, and then this residual. Okay, so these are all of the parameters that we need to estimate our random effects from. Okay, and in particular, if we remember that we're thinking about this D matrix here, right, where the D matrix is equal to the covariance matrix for our random effects terms, so for our BI. Well, these three parameters here, the standard deviations and the correlation, define our D matrix. So in particular, the standard deviation for the intercept is going to give us the sort of D00 term in our matrix. So it's the variance of our random intercept. Well, it's the square root of the variance of our random intercept, right? But so if we want to know sort of what is the estimated D, right? What's the estimated D matrix? Well, we could do, say, an R bind, and the first element is going to be this value squared, right? And then we need the covariance between the two terms, but we'll calculate that in one sec here. Then we would need the covariance again, and we also would want the random slopes term squared, right? So this is the standard deviation. If we square it, that gives us the estimated variance. So now we would need the covariance between the two. Now remember that the correlation, in general, the correlation is going to be given by the covariance divided by the square root of variance 1 times variance 2, right? And so by the same token, if we take the covariance or the correlation and we multiply by the square root of v1 times v2, which is the same thing as the correlation times by the standard deviation of the first one times the standard deviation of the second one, that gives us this covariance. And so what that means is by taking this negative 0.533 here, and multiplying it by each of these standard deviations. So I'm just copying and pasting these values in here. That will give us the covariance, right? And so then I can copy this down. It's going to be a symmetric matrix, and can sort of run this all down here. And we can take a look at D, and it's going to be this 2 by 2 matrix, right? Where we have our variance of 0.0122, and then the second variance term is going to be this very small value. It's 5 to the negative 5th power times 10 to the negative 5, and then their correlations between the two of them are 0.0004 roughly. And so that's our D matrix, right? So that sort of gives us the full parameterization there. In terms of our sigma squared value, so the sigma value we get in that same table, come up here, and it's the residual term, right? So the residual term squared gives us our sigma squared value. So this is 0.06. And so if we're estimating what the variance is, we would take sigma squared and we would see that it's 0.0036 roughly. Okay. And so that's going to be the sort of general way of reading off those random effects parameters. Now we might be interested in asking ourselves, does this model seem to need both the random slope and the random intercept, right? So if we look at D again very quickly here, we can see that the random slope has a variance that is very close to 0, right? It's 0.00005 roughly. And so, you could ask yourself, do you actually need that term, right? can the random slope be dropped? And, this is resulting in a hypothesis test of the variance of B1I equals 0, right, under the null hypothesis. So if you remember from the last lecture, this is a hypothesis that we have to be careful about testing, but it's one that we might be interested in. Do we actually need a random effect of age? And so there's an easy way of doing this. The first situation that we do here is we just fit our reduced model, right? So we'll say model1.reml reduced, and we're going to update model1reml. And here we're updating the random term. And in this case, we're going to drop our age term, right? So we're dropping the random slope and we're just nesting within ID, okay? And so we can fit that model. And now, in theory, we could call the ANOVA between model1 reml and model1 reml reduced, right? And this is going to output a test statistic here. It's the likelihood ratio test is a little bit hard to read off because of the size of the output here, but the test statistic is being computed as this 73.7581, and it's saying that the p-value is less than, so the p less than 0.0001, right? Now, what we have to watch out for is that this p-value is going to be incorrectly computed. And the problem is that this p-value is being computed based on a chi-square 1 distribution. And we saw in the last lecture that we actually need to use a mixture chi-squared. So it's a mixture of a chi-square 1 plus a chi-square 2. And these 2 degrees of freedom are based on the number of random effects that are in our first model and in our second model, right? So this model 1 reml has 2 random effects, so we get the 2 degrees of freedom. The reduced model has 1 random effect, so we get the 1 degree of freedom, right? So we actually need to be using a chi-square, a mixture chi-square distribution. Now on the course website, you should find a function or a file that has some helper functions in it. So I'm going to copy and paste those helper functions in here and just briefly explain them to you. But the first one is this Q mix chi-square, and it's going to take in a degrees of freedom 1, a degrees of freedom 2, and a Q value. And basically what it's going to do is it's going to return the test statistic result for the specified confidence level. So if you want to know what is the maximum test statistic value at a 5% level, what we could come in here is we could say Q mix chi-square, degrees of freedom 1 is 1, degrees of freedom 2 is 2, and if we're testing at, say, the 5% level, then this is going to output 5.14 roughly. And so any value larger than 5.14 is going to mean we reject the null hypothesis. So of course, with our computed value of 73, we're going to be rejecting the null hypothesis anyways, but that's what that Q function does. And then I also have a P mix chi-square, right? And that's going to sort of do your p-value computation, or 1 minus your p-value computation, in the same way that you would use p chi-square to do a similar thing, right? So I can come back up here and I can say our p-value is going to be 1 minus p mix chi-square. Degrees of freedom 1 is 1, degrees of freedom 2 is 2, and then our w in this case is going to be equal to this 74 value. And you can see that we actually end up getting basically 0 output anyways. So in this case, it didn't actually make a big difference, and that's because our test statistic is very far from the critical value. But if you had a test statistic that was closer, you may have found that it's going to give you the wrong p-value. And so you have to watch out for that. You should use those helper functions that are posted on the course website instead. Okay, but so all of that taken together means that we reject the null hypothesis and we cannot drop this random slope term. Okay, so even though it seems like the variance is very small, that's still a highly significant difference in the variance. Okay. And so that's what we would want to do there. Now, the next component is a component that we have not talked about very much in this course yet at all, but it's, sort of something that has been covered in your previous courses, and similar ideas are going to hold here as well. And that's this idea of diagnostic plotting. Okay, so if we want to know how well does a model fit, we've used hypotheses tests in the past to sort of take a look at that, but what we have not done is actually sort of used any plotting to say, are our assumptions valid? Now, this is less of a big deal when we're doing GEEs, and that's because we actually only need to get the mean correctly specified there. We're not specifying a distribution. We're not making any hard assumptions about the variance or whatever else. However, in this case, we have to make a distributional assumption about the random effects terms, a distributional assumption about the error terms, as well as an independence assumption about those two different sources of variation, as well as assuming that we have the form correct, right? So there's a lot more going in. And if any of those things are incorrectly assumed, then we might get into this situation where the model is totally unacceptable. And so as a result, what we will want to do is actually do some diagnostic plotting. Okay, and so I'm going to run through a handful of different plots here. We're going to go through them fairly quickly because, again, I assume that you're used to looking at these diagnostic plots. But if not, always ask me questions and play around with them a little bit, or take a look at some of the text materials, which would go through more examples of these. But the first thing that we want to do is take a look as to whether or not the errors are independent of one another. And so there are sort of two main ways that we're going to think about doing this. And I'm going to show you both of them here because the first one's going to make it look like it's a problem, and then we'll sort of explain why that's not so bad. But the first idea is that we can plot the autocorrelation function. So if we call ACF in R, that's going to give us the autocorrelation. And all we have to do is we have to just pass in the object. So in this case, let's say we're doing all of this on the model 1 REML fit. Right? We can pass in an alpha value here, which is just going to give us some confidence bands based on sort of whatever confidence level we specify. And if I run that plot, we can see we get this ACF plot. Now, if you haven't taken a time series analysis course yet, it might not be clear what we're looking at. But essentially, we want to see that no legs here, except for this leg at 0, this bar that's jutting up, go outside of these confidence bands. And we can see that very clearly. We do have legs popping outside of these confidence bands. And what that would seem to suggest is that we have an independence assumption violation. Now, the problem here is that these ACF plots are really only useful if you have evenly spaced data. And we talked about how for this data set, we do not have evenly spaced data. And so instead of using this ACF method when you have evenly spaced data, so this is likely inappropriate for the data we're looking at here, but it might be appropriate if you have nice balanced data. Instead, we might want to use this variogram function, okay? So we can call variogram. We pass in the model object that we fit. We also pass in the form of it. And so this is going to be whatever form we specified for our random effects here. And then we also want to specify the res type, which in this case will want to be Pearson. So this is just what form of the residuals are we looking at. And we're always looking at Pearson residuals in this course. So we can run that, and that's going to create an object here. And then we can plot the object. And so I'll call plot VG. And what I'm going to also specify is sigma equals 1. Now, what that's going to do is when I actually call this plot and we open it up over here, you can see this dotted line is at 1. Well, that's what that sigma parameter does. Now, what we know is that a variogram right here, we can actually take a peek at, if you were to take a peek at what this is actually doing, it should be randomly varying around 1 if the model is correctly specified. Okay, so you shouldn't see sort of any systematic trends in it. It should go up and down around 1 and always sort of be hovering there. Now, we might have a little bit of issues in this plot, just, there may be some trend, but honestly, taking a peek at it, it looks more or less okay. To me, we might have small issues, but it definitely looks okay to continue with this analysis as it goes right now. But if you were to see something that is, very different from this one line, then you might want to take a better look at sort of the independence assumptions. Okay. Now, the rest of these plots are all plots that I actually assume you will have seen before, regardless of whether you've taken time series or not. And so we can just call a plot on our object itself to get a residuals versus fitted values plot, right? So if I call plot on model 1 REML, and I just run this here, this should be a plot of the fitted values versus the standardized residuals. And what we're looking for here is there to be no pattern. We shouldn't see any trend. If you see a trend, then there's likely structure that you're missing in your model. And here, again, it looks perhaps not like the best fitted versus residuals plot you've ever seen, but it certainly, other than a few points that maybe shouldn't be hanging out down here, it looks more or less okay, right? Like the bulk of the points are sort of forming this nice cloud up there. And so we'll say that the fitted versus residuals looks okay. We can also take a look at the a QQ plot for the residuals. And we know that the QQ plot for the residuals should approximately look normal, right? So what I'll do is I'll call a QQ norm, and we'll say pass in the object, so model1.reml, And then we pass in, you can pass in this structure here where what I can do is I can call the residuals function, and that's going to actually get me the residuals, but I want them to be type of Pearson, right? And so if I run this, we should get this QQ plot here, right? And we expect this to be a straight line on y equals x. Now, here is where we start to see actually some issues, right? So I certainly don't think that this looks like a perfectly straight line. It looks like we probably have some tail issues in the data down here, right? And that was actually similar to what we were seeing with this fitted versus residuals, right? So it's not a perfectly straight line. I would think that probably it looks like there's likely some normality violations, and that might be a concern, right? We might be missing some tail behavior that we would want to take a closer look at, right? But for the sake of the video and sake of sort of showing you sort of everything that we might want to do, the next thing that is a good habit to get into is plotting our random effects, right? So if we plot the random effects for the model 1 REML, so again, RANEF here, RANEF, is going to give us the random effects that have been estimated from the model. We also have, and we used the fixed effects function as well, right? And that gives us our fixed effects, but the random effects is going to do a similar thing. And if I plot here and pull this over, you can see that we have the two plots for the two random effects. And essentially over here, we're having the ID. So each of these is going to be estimated for a single individual. And then same thing for the intercept as well. And so if we're thinking about it, we've said that those should be normally distributed on the population and they should have mean 0, right? And so you can see here, it does look to be sort of a fairly large mess, and that's sort of exactly what we would like. And they're spaced roughly around 0. Again, we might have, you know, slight skewing to the negative side on the age effect, but that doesn't look super problematic. So here, our random effects terms actually look pretty okay. Now, if you have trouble reading that kind of plot, we could also call QQ norm on the model1.reml, where we pass in, instead of it being called to the residuals, we just call the random effects on this model, right? And so if I run that, you can see that now we get these two normal QQ plots, and these look a lot better than the previous one did, right? Again, you expect them to sit on this straight y equals x line, and these ones look maybe like there's some issues, but more certainly straighter than the residuals terms looked. Okay. Now, we could also make plots of, say, the observed versus the fitted, or the observed versus the fitted by the subject, right? And so those plots, again, you've seen these types of things before. So I can go plot model 1 REML, and maybe I want to plot the log of the fixed, the FEV1, and we're going to say this across from the fitted values, right? And these should roughly pass around the line y equals x, and so I can add that line to this chart by adding AB line C01, right? And so now we have this observed versus the fitted values, and you can see we get nice fit around the line, so that the fit of the model appears to be quite good as well. You could also think about plotting this, the same plot, say, subsetted on ID, right? And this is going to take a little bit longer to plot here because we have quite a few IDs. But, and in this case, the subsetting on the ID might not be the most appropriate variable. But if we had a treatment variable, for instance, you might want to subset on treatment, and then you could see inside of each of the treatment classes, does it look like we're getting a good fit? I'm not sure that this plot's going to want to load for me right now. Yep, we get the session aborted. So I'll start this new session up and quickly get back to where we were at. But that plot should probably run for you if you're not recording a video at the same time. So as I get back to where we were at before, that sort of gives us all of the diagnostic information that we likely would want to see in those plots. So I would encourage you to, get used to looking at those types of plots, thinking about what each of the different plots is going to be able to tell us, what they're not going to necessarily be able to tell us, and that type of thing, right? And after you've sort of done some good diagnostic plotting, we can start to think about doing intervals and prediction, okay? So the first function that I want to bring to your attention here is actually the intervals function. And so if you call intervals on this object that we've fit here, right? So I literally call the intervals function on model1.remlsa. And assuming that I got all of my code run again, what you can see is that we actually get 95% confidence intervals for the fixed effects, which is giving us this lower, the estimated value, and then the upper, as well as for the random effects parameters, right? And so coming in here, just by calling this intervals function on this model, we sort of can do all of the inference on each of the parameters alone that we would want to do, right? And so just quickly scanning through here, you can see that this log of baseline height does not appear to be significant because it contains 0, right? And then we could come down here and take a peek at what the sort of intervals on those random effects terms are as well, right? Which is going to be interesting for us in light of our discussion on the random effects terms and which ones matter and which ones don't seem to matter and that type of thing. Now note that, again, we're going to always sort of be constraining these random effects terms away from 0, so the confidence intervals are going to be a little bit wonky, but it gives you some sense of, you know, at the smallest level versus at the upper level, what are the effect sizes that we're sort of talking about there. Okay, so doing confidence intervals on parameters, super easy. Doing confidence intervals on the parameters of the random effects terms should be super easy as well. The last thing that I want to talk about is this prediction, right? And so in the case of a mixed effects model, you can think about predicting at two different levels, right? So you can think about predicting the average in a population going forward, right? If you just had someone who had a particular set of covariates, you can predict what their average outcome is going to be. But for any specific individual, you could also think about predicting. And there we saw, you know, using the BLUP and then plugging that back in to get that y hat, that's going to do an individual level prediction based on the specific values, right? So the way that we can do this once we have a model fit in R is just going to simply by using the predict function. And so the idea is that we want to define a new data frame. And the new data frame is going to contain all of the sort of values that we want to predict out. And then we just pass it to the predict function. So I've gone ahead and made a new data frame here. And I'll read through sort of what we're doing with it, right? So I'm just defining this new data, and it's going to be a data frame. And into it, I have to pass a value for each of the different parameters that are included in our model. So we have the ID variables. And you can see that I'm using an ID of either 1 and then 3 terms at 25. Right, and so the first individual in this data frame is going to be individual number 1 from our data set. And then the next 3 rows are going to correspond to predictions made for individual number 25. The age can be whatever age we want to be predicted at, right? And so if we look at age here, I've set it to 18 for each of them. And so we're trying to make a prediction for individual 1 when they're 18, or for individual 25 when they're 18, right? And then for height, of course, that's going to be when they're 18, what is our height that we want to predict their outcome for? And so we're going to have 1.54 for individual 1. And then for, this shows why I have 3 different rows for individual 25. You can see that we have either 1.85, 1.7, or 2. So it's sort of this range of heights. And I'll show you why I'm picking that out for those individuals at this point. And then baseline height and baseline age, they were actually observed in the data set. And so I've just copy and pasted the relevant values here. And so if I define this new data frame here, you can see that I come down and it just gives us a data frame that looks kind of like our air pollution data frame. And, but in this case, it's sort of made up data. Now for individual 1, now that we have this data frame up here, you can see that we stopped observing them in the data set when they were 16.3 years old, right? And they were already 1.52 high. And so then basically what I'm suggesting is that they only grow another 0.02 over the remainder of the time in this study, but we want to know what is their lung function going to be predicted when they're 18 years old, okay? Now, the other person is individual 25, and so if I just scroll down through this data a bit here, you can see that individual 25, we actually only observed 2 different time points for them in this study, right? And so we observed them when they were 8 and when they were almost 9 years old. And so my thinking here is just that, you know, we might still care what is their predicted value when they're 18 years old, but that's 9 years later, right? So we have a lot less information about them. And so maybe we want to see a range of their scenarios when they're, you know, either 1.85, 1.7, or 2 meters tall at the end of it. Right? But so anyways, you could fill out this data with whatever you want, and then we can come in and use the predict function. So the predict function is going to take in the model that we want to predict from. So that's model 1 REML in our case. The new data, which in our case is new underscore data. And then we need to predict at a level. And so we can specify either a 0 if we want it to predict at the population level, a 1 if we want it to predict at the individual level, or both a 0 and a 1 to predict at both levels simultaneously. So let's do that. We can run this. And you can see that for each of the rows that we just specified in our data frame here, we get a predict fixed and we get a predict ID. Now, if we had just specified this 0 and run it again, then we're just going to get out the fixed predictions. And if we had just specified a 1, we're just going to get out the individualized predictions. If we specify it both, then you have both the fixed and the predicted. And so what we can say here is we can see sort of whether we are predicting the population average or whether we're predicting the individual average. So yeah, this predict function is evidently quite useful for making our predictions. But again, that's just taking what we had talked about in the conceptual lecture and sort of pushing that forward into the actual code that we're used to using here, right? And so if we actually wanted to try to interpret what these predictions were a little bit, we could see that for the first individual here, this prediction, 0.99, is actually slightly higher than what we would predict at the population average level. Whereas for individual number 2, we can see that no matter their height, no matter their predicted height, they're actually being estimated under the population average. And so what we're thinking there is that for this or individual with ID 25, that their random effects are going to be negative. So they're actually sort of pulled below. They're a lower responder than the population would guess, right? And so you could sort of think about doing that. But that essentially should give you all of the tools you need to work through a data set. We sort of covered a lot of ground here, and I would really encourage you to either play around more with these data or to download one of the other data sets from the course website and try to work through similar situations. Again, take a look at the helper functions that are uploaded on on the course website, along with all of the other data sets that are up there. There's a whole lot to play around with. And so if you have any questions with anything that was covered here, please do ask away. And otherwise, I will see you all in the next lecture.